Okay, welcome to today's lecture. We're going to introduce the concept of graphs. Graphs are really important data structures. They're used throughout computer science, and they allow us to represent relationships between objects in the real world or in the virtual world. And you can represent relationships such as two things are connected, like B is connected to C, like we see here, and C is connected to D, like we see here. And we know that because of this and this. These are edges. But in addition to these two and these two being directly connected, B and D do not have a direct connection, although they do have a connection through a path via C or via A. Okay, so this allows us to represent all kinds of pairwise relationships and then expand those pairwise relationships into more distant relationships. More formally, a graph is mathematically defined as a pair V and E, where V is the set of vertices and E is the set of edges. And the vertices are also called nodes. And I want to point out that when you're talking about multiple vertices, we can say vertices or vertexes, but the singular is always vertex. These edges can be directed or undirected. When they are undirected, they can be traveled. You can think of them as being traveled as in either direction. If they're directed, you can think of them as being traveled only in one direction. Edges can also be unweighted, as you see here, or they can have weights, meaning some sort of cost or distance associated with the edge. So down here, this is an undirected and unweighted graph. Most of the times when we've talked about algorithm analysis in the past, we've used the term N to describe how many items there are that we're concerned about analyzing. Like the length of the input is N. But now we have two quantities to describe the size of a graph. The number of vertices, which is the size of the set V, because V is a set of vertices, and so we use this cardinality notation to denote its size, and the size of the set E, the set of edges. And there could be, for a given set of vertices, there could be many edges or very few edges. So these two quantities are related, but they're not the same. We will use these two terms, V and E, to do our analysis now instead of N. So we won't talk about an N log N algorithm. We'll talk perhaps about an E log V algorithm, or we'll talk about a V plus E algorithm. And for simplicity's sake, even though we should be using this cardinality notation, where we use the vertical bars because V and E are sets, most of the time we'll leave those vertical bars off and just use V and E directly when it's clear. And that will be most of the time. So what are graphs useful for? Graphs can represent all kinds of things in the real physical world. They can represent road networks like this picture I have here, where you could think of each intersection as being a vertex. And you can think of, if two vertices share a road between them, then they are connected by some edge. And, different vertices, like you could have a vertex here and a vertex, say, here, and they share an edge, which is this road that goes between them. This is very difficult to do with my stylus, but you get the point. Okay. Computer networks are another good example of what a graph could represent. Each node in the graph could represent a computer, and a connection between two computers, either by a Wi-Fi connection or an Ethernet connection or some other type of connection, could be an edge. Airport flights, if you're trying to get from city A to city B, you might have to go through an intermediate city, city C, right? If you're trying to fly from Waco to New York City, you're probably going to have to fly through Dallas first. So the flights between cities can form a graph where the cities themselves are the nodes and the flights are the edges connecting the cities. Now, a less intuitive idea is that course prerequisites can form a graph. If I have multiple courses that I need to take, and some of them depend on others, that can form what's known as a directed acyclic graph. It's certainly a directed graph. So if I have a course A, and I have a course B, and I can't take course B without having first taken course A, then I might have a graph that indicates that relationship like this. So B is depends on A as a prerequisite, and maybe B is a prerequisite for another course C, and maybe C also has another prerequisite called D. Okay, so this prerequisite, the prerequisites that we have in courses can be encoded as a graph, and there's lots of others. Now, as I said, we can have directed or undirected graphs. Here's an example of an undirected graph like we've already seen. If I added directions to those edges, then it might look like this. And in this particular case, if you look at this edge, it can only be traveled from A to B. And notice there's no way to get back from B back to A. Whereas in this undirected graph, this edge is undirected, so it can be traveled either direction. So notice that in this graph, once you leave A to go to either B or C or D, you cannot get back to A. This, I'll mention, is a particular type of example, or a particular type of graph known as a directed acyclic graph. It's directed, the edges have direction, and it's acyclic. There are no cycles in this graph. In other words, there's no way to leave a vertex and come back to the same vertex. And oftentimes, we abbreviate that as a DAG, D-A-G. Okay. We can have costs on the edges, as I mentioned. So we might notate that, or we do notate that on the edges themselves when we draw the graph. So this edge right here from A to B has the property that it has a cost or weight of 3. So if I wanted to go from A to C, I could do so in at least 2 ways. I could go directly from A to C, which would cost me 8. Or I could go from A to B and then to C, which would cost me a total of 12. When we talk about graphs, it's important to think about how we represent the graphs. There are 2 primary ways that we can represent a graph, in memory, I mean. And the 2 are called the adjacency matrix and adjacency list. Adjacency here just means 2 things that are adjacent to one another or next to one another or connected to one another. So oftentimes we'll just talk about the matrix representation and the list representation. And these 2 representations have significant impact into how we think about graphs and how much memory they use and how fast our algorithms run. So it's really important to understand these. The adjacency matrix representation is a matrix. So if our directed graph looks like this, our adjacency matrix would look like this. We think of this as this is the from, and this is the to. Okay, so if I wanted to go from vertex A to vertex C, I would look in the graph at row A, column C, and I would notice that there's a 1 there, indicating that there is an edge from A to C directly. Notice also that if I looked at from C to A, there is no edge from C to A, which is, of course, notated in this diagram. Okay, so this is the adjacency matrix representation. We can represent this in, say, C++ as if we have, oftentimes we'll notate our vertices in these lectures as A, B, C, D, as letters, but when we implement it in code, we'll usually use indexes for these same vertices. So instead of calling this A, this vertex A, we probably call this vertex 0, vertex 1, and so on. So, and we might need to maintain a mapping between the index, the number, and the name separately from the graph itself. But so that's the point that we're making here. We give each node an index from 0 to v minus 1. And then we could represent that matrix as a vector of bools. And this would be in case, like the graph that we have illustrated here, that we have an unweighted graph. So every entry in the matrix represents true or false, whether or not there is an edge from this vertex to this other vertex. But if we wanted to deal with a weighted graph, so in other words, if we wanted to add weights like 3 and 5, yeah, oops, sorry, this notation software is not always perfect. There we go. If we wanted to deal with a weighted graph, then we could add, instead of dealing with Booleans at each entry in the matrix, we might put an integer or a double or whatever is your representation for a weight. Now, the question then becomes, what happens in a weighted graph if there is no edge from some vertex to some other vertex? With a Boolean, it's clear, it's false. But with an integer, what should we use for that integer value to indicate that there is no edge? For example, from up here, we have no edge that goes directly from B to D. All right. How do we indicate that in our matrix? Well, when we have a Boolean representation, then we just notate that with the fact that there's a 0 here. But if we were using an integer representation for a weighted graph, if we put a 0 there, does that mean no edge? Or does that mean an edge with a cost of 0? Well, it's not clear, right? So if you want to represent graphs that have 0 cost edges or even negative cost edges, negative weight edges, then you might need to use sort of a pair of both of these. One to indicate which edges actually exist, and if they exist, what their weights are. Or instead of using two matrices, you could put them in one matrix with a pair of a Boolean and an integer together, or whatever your weight type is, integer or float or double. Now, the other representation, the other major representation, is an adjacency list representation. And unlike, let's go back for just a second, the matrix represents every possible edge that could exist, but only puts values in for those that do exist. But notice that we explicitly have to name that, oh yeah, there is no edge from A to A, and there is no edge from C to B. Right? All of these potential edges are explicitly enumerated and given true-false values. With the adjacency list representation, this representation is used or represents only the edges that actually exist. So if you look at the same exact directed graph, we have only the edges that actually exist. So from A, we have edges to B, to C, and to D. So this list right here represents the fact that there are 3 edges from A to B, C, and D. Okay, so this list represents A as the source and B as the tail, or A as the source and C as the tail, or A as the source and D as the tail or the destination, right? So from B, we only have one outgoing edge to C. From C, we have one to D. And from D, we have no outgoing edges. So here's a way we could represent this in C++. We could have a vector of lists of integers, where this integer is the index of the destination node, right? Because we are not using letters A, B, C, D, we're actually using integers to represent those vertex indexes. Now, that's for an unweighted graph. If we have a weighted graph, we could use a vector of list of pairs, right? Where the first pair, the first integer in the pair might represent the vertex. Oops. That's the vertex. And the second integer might represent the weight. Okay? And that weight could be an integer, or it could be a float or a double or what have you. Now, the advantage of using this adjacency list representation is if we have a lot of vertices but relatively few edges, then we only have to represent the edges that actually exist. So it is what we call a sparse representation. It is more memory efficient in some ways. Okay. Now, let's talk for a minute about how many edges could possibly exist in a graph. Uh, in other words, let's try to relate a bound on E, the number of edges. Clearly, the number of edges is greater than or equal to 0. Well, obviously, a graph might have no edges, in which case E is 0, and clearly E is going to be a non-negative number. Okay, but what is the largest number of edges that could be? Well, for a hint at that, take a look at this fully connected directed graph. Every vertex, all of the 4 vertices, has a connection not only to itself, but also to every other vertex in the graph and an incoming edge. Okay, so that gives you a hint that the number of total edges that could be in a fully connected directed graph is v squared. Okay, so we now have a bound on E, that E is a value between 0 and v squared. Okay, including if you include self-connections. Now, when a graph has a lot of edges, we call it a dense graph. This right here, this example, this is as dense as a graph, as dense a graph as you can get. If a graph has no edges, clearly that's not a dense graph, and it would be what we call a sparse graph. Okay. A sparse graph has relatively few edges. What does that mean? Well, there's no hard and fast definition, but it's clearly much less than v squared. Okay, so graphs can be more dense, more sparse. There's no hard and fast dividing line between these two, but I would say if the number of edges is close to the number of vertices, that would be sparse. And if it's closer to the number of vertices squared, that's definitely dense. In the middle ground, well, there's no dividing line there. So these are useful terms, but they are not precisely defined terms, sparse and dense. But we will use them quite often when we talk about the running time of different algorithms under different conditions, whether on a sparse graph or a dense graph. Okay. Now, let's talk about the memory usage for these two different representations. An adjacency matrix, again, represents all possible edges. And so an adjacency matrix uses v squared memory. Okay. Always. No matter how many edges actually exist in the graph, an adjacency matrix always uses v squared memory. An adjacency list uses enough memory to represent all the vertices plus all the edges, right? There's a list for every vertex, and all of the lists together contain all of the all of the lists together contain all of the edges. So an adjacency list uses v plus e memory. Now these are big O sense terms, right? It's v squared times the size of whatever the element of the matrix is, and it's v plus e times the size of what each of those edges cost. So the question then becomes, which of these representations, matrix or list, is better for sparse graphs, and which is better for dense graphs? Well, I hope it's clear that when there are very few edges, when we have a sparse graph, a list is going to be better for representation for a sparse graph because it's going to use a lot less memory, and it's going to represent only those edges which actually exist instead of all the possible edges. But if we have a lot of edges, up to v squared edges, then a dense graph is going to be more usefully represented by a matrix, because we're going to have on the order of v squared edges anyway, so we might as well explicitly put them all in one big matrix, which we can access quickly. So this matters because not only does it affect the amount of memory that we would use for the representation, but also the runtime of different algorithms, or I'm sorry, the same algorithm will have a different big O runtime depending on the representation. So we'll see later on in these lectures that some algorithms, the identical algorithm essentially, will have v squared running time using a matrix representation, but e log v running time for a list representation. And these can be very different depending on the values of e and v. So let's think about some very simple queries and how much time they would take with these two different representations. Okay, how fast can we do the following? Well, the answers are already here, but let's talk about them. The first question is, how quickly could you determine if an edge exists between A and B? In other words, is there an edge directly connecting nodes A and B? For a matrix representation, the cost is order 1 because you have to go to row A, column B, and your answer is right there. Okay, but what about for the list? For the list, what do you have to do? You have to go to the list corresponding to vertex A, and then you have to search each element of that list and see if B exists in that list. How long could that list be? Well, the vertex A could be connected to every other vertex in the graph, which is V other things, or V minus 1 other things plus V plus 1 for itself. But the point is that you might have to search order V things in a list just to determine if there's an edge from A directly to B. Okay, so that is a significant difference if the question that you're asking in the middle of an algorithm is there an edge between A and B? You can answer that much more quickly with a matrix than a list. Okay, what if our question is, let's list all of the edges in the graph. Now, how many edges are there in the graph? Well, there are E edges in the graph. If we were using a matrix to do this, we would have to walk along all parts of the matrix, all entries in the matrix, and say, are you an edge? Are you an edge? Are you an edge? And identify which of those are edges and which are not, and list only the ones that are edges. And that would take V squared time. If we're using a list, we're going to spend, I wrote here order E. I would actually like to amend that to say V plus E, because we have to look at every list, and there are V lists. And then we have to look at, in total, E edges. Right? There are E edges across all the lists if you sum them all up. And so this is essentially V plus E, but the dominant term is probably E here. So again, if E is small, if this is a sparse graph, then V squared might be much larger than E. And so a list representation might be much quicker in this situation. Now, of course, these might be identical if the number of edges is close to V squared. So again, it depends on the sparsity or the density of our graph and also on the representation. But the point is that the representation that we use and the sparsity or density of the graph changes the efficiency of our algorithms. Let's talk about some definitional things. First of all, let's talk about paths in a graph. A path in a graph is a sequence of vertices connected by edges. Okay, so a path is A to B, but a path is also A to B to C to D. B to D is not a path because there is no direct connection from B to D. But if I wanted to get from B to D, I might go from B to C as an intermediate vertex to D, right? The path length is the number of edges in the path, okay? And that's as opposed to the path cost, which we'll talk about in the next few slides. So in this case, the one I've highlighted, B, C, D, the path length is 2. It's 3 vertices, but 2 edges. Okay, in a weighted graph, we can talk about the path cost, not length, but cost. And the cost is the sum of the weights along the path. So if I were going from B to D again, I would go from B to C to D, and the path cost for that would be 10. Okay. A few more definitional things. A path is called simple if it has no repeated vertex. A path can be a cycle, which it means it starts and ends at the same vertex. And a cycle is a simple cycle if it only repeats the first and last vertex, and no, it does not repeat any other vertex. Last definitional things. Connectivity of a graph. Well, the terms are a little different depending on whether we're talking about undirected or directed graphs. So let's start with an undirected graph. An undirected graph can either be connected or disconnected, okay? So here we have an undirected graph which is connected. What does that mean? It means that from every vertex you can get to every other vertex. there is no break in this graph. However, if I were to cut off this edge, if I were to remove it from the graph, so D is still a vertex in the graph, it's just that D is disconnected from the rest of the graph, then that graph would be called disconnected, okay? So a graph is connected if every vertex can get to every other vertex, or it's disconnected if there's a split between some set of vertices and some other set of vertices, or multiple splits, okay? So this is a connected graph, but if I were to break the graph like I did here, or if I were to delete these two edges, then I would have, again, a disconnected, undirected graph. Now things are just slightly more complicated, or at least more nuanced, with a directed graph. With a directed graph, we can say that they are strongly connected, weakly connected, or disconnected. Now the sense of disconnected is the same sense that we had over here for an undirected graph. So in other words, let's start there. If I were to just lop off all three of these edges, I would end up with a disconnected directed graph. Okay, so that's disconnected. This graph that I've drawn happens to be strongly connected. And that means that every vertex can get to every other vertex, which is the same sort of definition that we had for undirected connected graphs. But when it's directed, we say it's strongly connected if every vertex can get to every other vertex. And let's see why that's true. If I start at A, I can get to B, I can get to C, and I can get to D. If I start at B, I can get to C and D, but also I can come back to A and go to B. And so we see that there's a cycle here, A, B, C, D, and back to A. And so every vertex can reach every other vertex. So this graph is strongly connected. Now, a weakly connected graph is a graph which is not strongly connected, but would be connected if I were to remove the direction of the edges. So let me give you an example. Let's pretend that we were to delete this edge. If I delete this edge, I no longer have a cycle in this graph. But what I do have is a graph that looks very much like this undirected graph. However, all the edges have direction. Do I have a strongly connected graph? No. But if I were to remove the directionality of all of these remaining edges, in other words, if I just made these undirected edges, so A and B can go back and forth along this edge, and B and C can go back and forth along this edge. Since that resulting undirected graph is connected, this is what we call a weakly connected graph. It's not strongly connected, but if we were to take the directionality away from all the edges, it would be connected. Therefore, it is weakly connected. And that's it. So next time we'll start talking about some more advanced topics regarding how we can move around and find things in graphs.